for which fn equals 3. Okay, yeah, A and B look like... Okay, so A looks like it's gonna be... do you actually want me to do A and B? I think that just involves me writing out enough elements, right? So perfect powers 4, 8, 9, 16, 25. Those are the ones less than whatever. 30, 27. There's one more. So A looks like it's just exhaustive search. Like I don't see. You start with 30. You do casework on the biggest thing. 14 is not doable. 5 is not doable. 21 isn't doable. Yeah. So I don't think there's anything to say for A. You just kind of check it. So B is the first interesting one. Okay. I want to show that there's at least one way. So here's my thought. Sum of squares are pretty good, right? Like, well, actually, sum of anything's pretty. Okay. So every integer is the sum of 4 squares, and then the only thing you're worried about is you can't use 1. Oh, yeah, right. Sorry, distinct. Okay, I don't know. Just how many base cases am I going to need for this? Actually, forget squares. Like, most integers are sum of binary numbers, right? It's just 1 and 2 are missing. So, okay. As long as it's 0 mod 4, I'm okay. So, I need some base cases. For 31, what did I use? 27 is 3 mod 4. I need a number that's 2 mod 4 in this list. That isn't a power of 2. So 9 can be my 1 mod 4 number. What's a power of some... No perfect powers are 2 mod 4. Ah, that's an issue. So when I look at when I look at 34, what happens? Oh, I can add 2 things to get something that's 2 mod 4, right? Like 9 plus 25 is 2 mod 4. Okay, there we go. So for all sufficiently large n, 1 of n minus 9, n minus 34, n minus 27 is the sum is divisible by 4. In which case you can use binary. I was thinking squares, but binary is pretty good. This idea applies to C as well. It does indeed look like it applies to C, because like once you have enough numbers, you can just do garbage like this, right? So I'm gonna look at S minus the powers of 2. So I want, what are the numbers that I have at my disposal? 9, 25, 27, 36. Uh, 49. I should just write it as here. 9, 2, 3, 4, 5, 6. Whereas power, that's cubes, whereas squares are 4, but I want the, okay. So 9 is a useful number. So is 25, 49, 7, 4, 6. 36 is a useful number. 49 is a useful number. 7, 8. Generalize multiples of 4 to get f of n plus 4 at least f of n. I see. Oh, yeah, that's pretty good actually. Okay, so here, claim f of n plus 4 is at least f of n, and the reason is wait a minute. Am I being duped? Why is that true? I don't believe. Wait, I'm not sure I believe. Look at the powers of 2 use. Yeah, but the problem is that if you have a representation of n plus 4, it does not need to use the digit 4, right? Like, it could use the 36. Like, there's representations of... Wait, hang on. No, I'm confusing myself. So, the claim is every representation of n will give a representation of n plus 4, or vice... Or do I want to go down? If you want to go to n plus 4, you want to assure that 4 isn't used. Yeah, I don't see why this claim is true, actually. Add 4 to binary stuff. What if I just use brute force? Is that a viable... Like... Oh, no. Okay, so let's see. What's the first time I get... So we have this binary idea, right? And there's going to be cases on things mod 4. Go back to Python. Yeah. Is today Python stream? So 9 is my most useful number, to be honest. 9. Subtract 9. Or subtract 25. Subtract 49. Or 9 plus 36. So, once n is at least 45... once n is at least 49, all the 1 mod 4 numbers will have some number of representations. In the 1 mod 4 case. This is only for 1 mod 4. These numbers are going to get really large really fast. Oh, wait, so what's the thing? If I have a representation, I throw in a 4. I add an extra 4 and then the binary regroups. I see, okay, fine. Binary regroup. Oh, sorry, I'm basic. For each representation, change the binary part to use more 4. To increase by 4. Okay, yeah, you guys are right. I should do that. So, ascending chain. So where do I think the worst case is? The worst case is probably the 0 mod 4 case, right? Like, it's so hard to get... Well, maybe it's not that hard. So what are things? So basically what I'm trying to do is write sets of things from the 25 plus 27, 9 plus 36 plus 27. Is there a shorter one? Oh, actually, just 36 works. I don't need to go that high. 9 plus 27, 36. What's the next smallest thing that's divisible by 4? Can I just add? $25 plus 27. So for n, at least 52. So I'm not making these bounds sharp yet because I'm not optimizing this because I don't know which residue class is the one that I care about. So for now, I'm just kind of doing the dumbest thing. So this is 9 plus 25. Perfect power will never be 2 mod 4. It's actually a 2 mod 4 case I think is the scariest. You need to add things that are... Yeah, all of these will always be divisible by 4. So 9 plus 25, 9 plus 25 plus 36 is probably up there. It's going to be the 2 mod 4 case to optimize, isn't it? Oh yeah, that's really bad. Is it 3 mod case? No, I don't believe the 3 mod 4, because there's a 27 that's pretty clean, right? So the 27 and then 27 add in the multiples of 4. Oh, actually, yeah, it's gonna be pretty big. Never mind, you're right. Oh wow, okay. Let's write out some more numbers. Still a rerun? No, it's not. Does this look like a rerun? I'm not sure what that says about the stream. People can't tell the difference between the rerun and the live runs. 121, 12, 13, 14, 15. Man, this is such a great problem for grinding. And put it on and everyone will hate me. 343, 7. So that's the cubes. The fifth powers are ludicrously large, right? 243 it starts at. So I'm not even going to bother writing the rest of them. Didn't I change the title? Did I not change the title? Why would people take grinding in the first place? So that they don't die on the test when an actual grinding problem? It's also fun in like a masochistic kind of way because the problems are so bad. They're so bad it's good kind of thing. It's a lot of the same reason people take anti-problems because the problems are so bad that it's funny. Anyways, 3 mod 4 might be the worst case. Is that right? So 125 is... Is there really no smaller one than 144? At that point, I almost want to just add 3 numbers that are 1 mod 4, which would be 9, 25, 49. That seems smaller, right? And at least 119. Don't forget 100 is allowed. Okay, what about 2 mod 4? So 2 mod 4 is I think the most confusing case for me because you really have to use at least 2 1 mod 4 numbers. Or you can do 3 plus 1 plus 1 plus 1. That seems really bad. That's like... Oh, Jesus. I feel very sorry for whoever has to grade this. Well, actually, it's not that hard to grade because you check if the answer is right. Alright, so 9 plus 25 plus... Wait, 49 is 83. 9 plus 25 plus 27 is 2 mod 4. 1. 70, 34. Wait, 71 is not 2 mod 4. Wait, something went wrong. 9 plus... Crap. I don't want to use a number that big though. Ah, what? How did I say I could get to 2? No, you can't do that. I want 49 and 81 versus 74 is smaller though. 25 plus 49. I mean, I don't need to optimize this because this is already good enough. For n at least... Yeah, this is n at least 74. So the hardest case is going to be the 3 mod 4 case. Because I have bounds here. But n equals 119... Well, 117 I bet is going to be the one that causes us problems. So, do I just bash 117? Or sorry, not 100, 115 is a 3 mod 4 number that we think will cause issues. It just slips under 125. There's 100 here. 15 doesn't work. Yeah, so 115 is looks like it's the culprit. Unless I can get a representation that's better than that. So also, I don't really think I needed this. I never actually used this, right? I think it's good intuition, but I don't think I used it in my proof. Okay, let's bash 115. So in order to bash 115 rigorously, as we would want to do on a contest, as far as actually trying to write this up, we would say we define a new function, let g of n be the number of ways to write n as the sum of a multiple of 4 and distinct powers in s minus powers of 2. So actually g of n is f of n, right? So, well, okay, actually, screw the notation. Go after 115. So, g of 115. So let's use casework on the largest number. The largest powers that are beneath this are 15. 81 is 34. Which does work. Can we just check 1 mod 4 and finish? Wait, what? Like I'm claiming that I need f of 115 equals 3. Did I? No, I think I can do this one by hand. This looks easy. So what we're 34 is 25 plus 9. One solution. Yeah, I think you just kind of write this tree out. 115 minus 49 is 66. Like, just show you can only get rid of 3 mod 4 things without powers of 2. I see what you're trying to say, I think. I feel like, yeah. The thing is, I think the sentiment is actually I wasn't very careful here, right? When I was kind of doing this. Well, actually, I know what the cases are going to be. 925.49. So, I mean, what if I wanted to compactify this? What would I say? I'm looking for. I want to show 115 is the sum of. There's so many cases though. CG. Oh, did we get 27? 27 plus 36. Did I miss something up here then? Nine plus 25 plus 81. Oh yeah, I can optimize this. 81. Okay, so we're actually going after 111. Thanks for the tip. Yeah, I figured something was okay. Alright, well. One 11 should have 3, right? Okay. 30. 30 has no solutions. That's the point. One solution. 62. 62. 28. 75. I would need. Thank you, Androme, for the follow. This is very laborious. Why fn plus 4 at least fn? I mean, it doesn't really matter, but the idea is binary basically. Fn is more or less essentially f of n is the number of ways to write the as a sum of binary, like a multiple of 4 plus random other powers. Okay, yeah. So this is look at cases on largest power. Okay, 111. I think that's it. If I didn't miss a case, so 62. It's like, what are the ways to write 62 as I need a 1 mod? Yeah, 62. 1 minus 81 is 30. No solutions because 30 is too small to write as 4 plus any of the other things. Okay, please say the answer is actually, so the answer actually 111, or did I miss a case? Where'd the chat go? Hey, did Twitch die? Oh no. Elegant solution. It was less bad than I thought it would be. When I first looked at the problem, I thought might not be possible by hand, but it's definitely possible by hand. Alright, cool. Cool. Let's go blow up some JMO problems.